Alright, so this graph shows the index of refraction as a function of wavelength of the color of light. And so there's not just one number that goes along with a material, but if you really look at it closely, you can see that it's a range of different indices of refraction depending on the color involved. So it says the index of refraction for a material will generally decrease with increasing wavelength. So violet tends to bend more than red light when passing into a refracting material. So if we have a beam of light consisting of red, green, and violet striking the prism, then the indices of refraction from the table would be given here. Red has an index of refraction of 1.43, green has 1.4, and violet has 1.37. So we want to see which of these colors could definitely not be seen by the observer. Alright, so let's figure that the angle of incidence for all of these colors is going to be 45 degrees. We'll call that theta 1. And then this, when we do Snell's law, would be theta 2. Now it might just so happen that the theta 2 could get close to 90 degrees. And if it gets close to 90 degrees, it could still emerge from the prism and be seen by the observer. But if that theta 2 ends up exactly 90 degrees, that would be what's called a critical angle for the incident beam, meaning that's when it won't emerge, but it'll just sort of head toward the boundary, and then it would like basically just travel along the surface itself. But it could be too that the bending would be so extreme that maybe the color will come in and it could only reflect, and there's no like solution to the Snell's law because you can't take the arc sine of a number that's greater than 1, as we'll see. Alright, so let's try Snell's law on each color. We'll do it for red first. For red, we want to use, let's see, N1 can be 1.43. And then N2 is just air, so let's just do 1 for that. So see, N1 is inside the prism. Okay, and then N2 is air, outside the prism. Alright, so we'll do N1 sine of theta 1 equals N2 sine theta 2. Alright, so for red, 1.43. Now for N2, we use 1, and then we'll just solve for theta 2. Okay, so the problem here with red is you get 1.01 equals sine theta 2. And if you try to do the sine inverse of a number greater than 1, you can't do it because no angle has a sine that's greater than 1. It does not exist. Which means that red cannot emerge when it's headed in at that angle. Okay, let's try green. Let's see if green can emerge. For green, we want N1 is 1.4. Alright, so we'll do N1 sine theta 1 equals N2 sine theta 2. 1.4 sine 45 equals 1 sine theta 2. Now we have 0.9899 equals sine theta 2. So you take the arc sine of that, you can get an answer. 81.9 degrees. Alright, so green comes in, and it does come out. I mean, it's just barely, but it does emerge. The red won't. The red will just hit and it could reflect. It can reflect off the surface boundary there. That's all it can do. The last one is violet, where N is 1.37. So I get 75.6 for that. So it looks like purple will have no problem escaping the prism at that angle.